Good. My name is Nicolai Josuttis. I am trying to enable the pointer. So, I'm involved in the C++ standardization for 25 years, written some books from the beginning. And in the beginning, I cared mostly for the library. Now I care for everything. The problem is they screwed up the language that much that I have to deal with that. So because I had problems using it in the library. No, just kidding. Oh, this is recorded. Too bad. Good. Now, we do a good job. We are 200 people now standardizing C++. Please note, this is not chief architect behind. We have 200 programmers with different ideas, different interests, different experience, and we do the best we can. And if you want to complain about the C++ standard, I will always say it's your fault, because you haven't been there. So come there and help us to make it even better. That's it. That's not the end of the talk. That's the end of the begin of the talk. It doesn't work that way. I have to put off my jacket. Smart pointers, no. Yeah, let's talk about smart pointers. Why do we have smart pointers? Well, because raw pointers suck. We have a lot of big problems with that. One of the biggest problems we have is polymorphism in C++. Although I yesterday introduced that we have a new option called variant, where we can avoid using pointers when we want to have polymorphism and heterogeneous collections. We still need it in various ways. So let's look at the motivational example for smart pointers here. Assume we have a hierarchy for polymorphism, so base class geometric objects, and then circle and line as a concrete class derived from that. And the point is, you only have polymorphism in collections if you use references or pointers. References are not allowed, so we have to use pointers in, for example, a vector. And when we initialize a vector of elements that looks like the following, let's create the vector of the elements. The elements are pointer, as I said. Let's create the elements. Don't create them on the stack, because if you create them on the stack and add the address of this element in the vector, the object we refer to is gone when we return the vector. So we have to create it on the heap. Here a line and a circle. We push them back into the vector, and we return the whole thing to the caller, and the caller might initialize an object and see here that all local objects are gone, but fortunately we created the objects in the heap. So we still have them, and we can use them and perform our polymorphic calls, for example here called draw. And at runtime, there is a decision which draw function to call, depending on whether we currently have a circle or a line here. Okay, so far so good. So the only problem we have left is, let's remove the elements. And there's an important thing here. It's not enough to just to call clear. If you call clear, you have a memory leak. You have to make sure that before we remove the elements, which are only raw pointers, we have called delete for the corresponding new call. Here you see one example to do it. Just start a loop over all the elements, which are pointers. We might not only call delete, we might also want to ensure that all the elements are null pointers now. So we iterate by reference over pointers so that we can call delete and then assign to the pointers the null pointer. So things like that happen if you use polymorphism with raw pointers. So how can we do better? There's one principle in C++ which is very important, RAII, resource acquisition is initialization, which means put something you have to clean up in an object so that a destructor can call the corresponding cleanup when it goes out of scope. So what we need here is something like a smart pointer that says whenever this pointer goes out of scope, let's then automatically call delete. And that's roughly the idea of smart pointers, that we have a way to say, well, instead of us calling delete, which might create some trouble, we might call it too late or too early. So let's decide the pointers what to do. And one thing we provided even before C++ 11 were shared pointers. Well, you could do that. And shared pointers also had another benefit. You could still have different owners, different pointers referring to the same object. So by using smart pointers, we implement a way that the compiler does the work for us and we make less mistakes. So we have two concepts of smart pointers in C++ since C++ 11. We had a third one called auto pointer. Please don't use it, we come to that later. And shared pointers and unique pointers that were both introduced with C++ 11. Let's look at them. So the first example is, let's use a shared pointer here. And a shared pointer, we introduced a type here for that, just the type definition. Cleo pointer is a shared pointer of geometric object. So this is a smart pointer now. And the smart pointer changes the behavior a little bit. First of all, the usual way to create it is use MakeShare. And what happens here is we create the vector, and then when we call MakeShare, two things happen. We create an object on the heap, and we create a counter. The counter might be bound to the object or might be not. MakeShare usually bounds them together, which is a little bit misleading in this picture here because they look like two different objects. We come to that later. But the key thing is, beside creating an object on the heap, we create a counter somewhere available over the lifetime of this returned pointer, shared pointer. So it also has to be created on the heap. So the two things there, the counter and the objects are on the heap, the rest is on the stack. I should use different colors there to make that clear. And then let's call another MakeShare call, which does the same thing for a circle. And now the trick is that this pointer is smart. And that means that it finds out how many owners we have, and when the last owner dies, the delete for the object will automatically be called. So we pass both shared pointers into the vector, and you see that this increases the owner count. So we share from two different positions. We point to this object. And when we then return it, we might even temporarily create a third pointer that temporarily also refers to the object, but this might be the returned vector if you create a new one and copy all the elements. But on the other hand, we leave the function, and that means that we remove all the local objects on the stack, which is both the LP and CP shared pointer, single objects, and the local vector of pointers here. This might be optimized, yes, I know. But the point is, yeah, we have a counter. We always know how many owners we have. And here, for example, currently we only have one owner for each object we have. So we can use it as an ordinary pointer. So if we iterate over all the elements, you can still iterate. The data type is const geopointer, but you can still use auto here, const auto, and even not see that you use a slightly different type here. And we have polymorphic calls because the arrow operator in a smart pointer is overloaded, that we, over a raw pointer internally used, call the right draw and decide at runtime which draw to call. That's it. And the good thing is, at the end, we clear all the elements in the vector, and now the magic happens. As you just saw it, clear just removes the elements, so we call the destructor of a shared pointer, which is the last owner of the element. So as we are the last owner, the moment we decrement the owner count to 0, we automatically call delete, and we have no memory leak. We delete it at the moment we no longer need it. That's, to some extent, just an implementation of reference counting in a data type. Good, so far. By the way, look at that we use MakeShare here. MakeShare has its drawbacks. There's a rumor in the community that MakeShare is always good. That's not true. We will come also to that. So instead of using MakeShare, you might do two steps. You might first call new for the objects and then pass the returned raw pointer to a shared pointer. And we will see why this is sometimes better than using MakeShare. What is the alternative? The alternative is using a unique pointer. And maybe we go to this alternative later. I already changed the order of my slides. That happens from time to time. So let's look first now into details of shared pointers. So with shared pointers, as I said, you can call new to create an object. So if you have a shared pointer and later on create new, call new, you have this object created and return a raw pointer, and then you pass the ownership of this from this raw pointer to a shared pointer, and that creates this control block. And the control block is created on the heap. And each operation you call is an indirect access to the underlying object. So far, so good. So if we assign this object to another shared pointer, like here, the other shared pointer can also access the element, and the owner counter goes to 2. If we leave the scope, the inner scope, we only have left the outer scope pointer, and if we leave that, we delete the pointer. So far, so good. That's a basic principle of a shared pointer. There are some good things, like you can define your own deleters. So that means that you not only can use it for resources created with new, you can also use that for resources created, for example, with an fopen or popen call, where we return another kind of pointer where we need some cleanup at deletion time. So here, for example, on the top, we call popen to open a pipe, and then we can specify, ideally as a lambda, or as an example in a lambda, that we call pleclose to clean up the resource. There's one concept here called weak pointers. So beside of shared pointers, we have another brother or sister of shared pointers, which is a weak pointer. Part of the concept of shared pointers, it is an observer that does not count as an owner. And so it uses the principle of shared owner and of smart pointers, but if you use it, it does not count as an owner. So an object will die if the last shared pointer dies, even if weak pointers still refer to them. But the good thing is you can find out when the weak pointer dangles, so you can ask the weak pointer, is there still an object? So why do you use that? First of all, to resolve cyclic references, cyclic pointers, because otherwise you would never clean up a combination of multiple objects, because there's always one owner. Like here, resource A points to resource B, and resource B points to resource A, and we only have a shared pointer outside pointing to resource A. So somebody needs resource A, and resource A needs resource B, but they have a back pointer, which is a very common case. Here we also use an observer to observe, is there still a resource A? So the moment we delete here the shared pointer, we have deleted the last owner of resource A, because the back pointer from resource B is not a shared pointer, does not count as an owner, it's a weak pointer. So that means we delete resource A, or indirectly, so automatically the destructor will call delete for the resource A, and that will delete the last owner of resource B, so that will be deleted, and that's the effect of deleting the shared pointer on the left side. There's still the weak pointer, and you can ask the weak pointer, is there still something available or not? This is important that we have the concept of weak pointer. There's a reason you have to take that into account, as you will see in a moment. Let's see how to use a weak pointer. Weak pointer looks like it is also a shared pointer, so you might assume to use it we need a pointer API, but that's not true. It does not use a pointer API, so here if we create something and have a shared pointer as an owner and then we have a weak pointer as an observer, you can't directly use the arrow operator to access the object you're pointing to. You have first to lock the object. And the lock will give you a shared pointer back. Why that? Because of multi-threading. Because while we are from an observer dealing with the resource R, and then the last shared pointer dies, while we are using it, we are in big trouble. So the trick is that lock creates a new shared pointer temporarily or not temporarily, and that means even if SP now dies, we still have an owner, which is P. As long as we have P, we can use it. And that's safe code even in multi-threading environments. So now with P, we can call a member function, and you can do that also in one step, creating a shared pointer from a weak pointer, but here you get an exception if the weak pointer refers to some object that is already gone. Please don't program it that way. There's also a member function. Is there still a shared pointer? Is there still an object? And because the answer might be old if you use it, so if the answer is true, then you call lock and call member without checking the return value of lock. You are using a null pointer here. This is not thread safe because between the call of expired and lock, that somebody might have deleted the last owner of the object. So do it the other way around. Good. This weak pointer has consequences for the concept and implementation of shared pointers. So let's look at this example. We have outside a weak pointer, we have outside a shared pointer, and then we have a shared pointer which we directly initialize with the return value of a call of new. And the point is, we have in fact two counters now because of weak pointers in the control block. In the control block, we have to count how many owners we have, and we have to count how many weak pointers we have. And the reason is pretty clear the moment we use this example. We have one owner, so let's assign this to another owner. So we have two owners now, and now let's assign this to an observer, to a weak pointer. So far, so good. So why do we have different counters? Because if we delete the first owner, nothing happens, just we decrement the owner count. But if we delete the last owner, we can delete the resource, but we can't delete the control block because the control block contains the information the weak pointer has to give us to explain, is there still an object or not? Otherwise, we have no memory to hold this information. So that means we still have to keep the control block alive. And now the weak pointer can tell us, no, there is no longer a resource. So if we try to call lock, it will give us a null pointer as a shared pointer, or non-initialized shared pointer. So only if the last weak pointer dies, the control block is gone. Okay, so we have two pointers, fine. So now we come to MakeShare. So in the internet and maybe also in the community, you always learn, let's always use MakeShare. It's always better. That's a lie. That's not correct. Because look at the same example I just went through by using a shared pointer. MakeShare. So the point is, the trick of MakeShare is, and that's one benefit of it, it calls not new twice, because we call new for the resource and we call new for the counter. It calls new only once. So it creates something like this. It allocates memory for both the control block and the resource. So we save in the control block a pointer and we save a call of new. So that's a good thing. That is faster and therefore usually better. So however, we have introduced a problem now. If we now copy the shared pointer to another shared pointer and introduce an observer to this resource, okay, everything is fine. But now let's delete the first owner, so by leaving the scope here, the inner scope. And now let's leave the middle scope where the last owner is valid. So now we have an interesting situation. We can delete the resource, but we have to keep the control block alive because there is the information for the weak pointer to give us an answer for does this object still exist or not. So we have to keep this control block alive, but the lifetime of the control block is bound to the memory of the resource because we only have allocated in one memory, one piece of memory. So that means we can't delete the memory. We can call the destructor, and we do it, but we can't delete the memory or free the memory of the whole thing, which means if you use MakeShare and you're using weak pointers, and your resources allocate a huge amount of memory, you have an interesting logical resource leak by not deleting or destroying all your weak pointers. If you just keep the weak pointers alive, the memory of your resources will never be freed. And I've seen that in at least one project where we thought we have a memory leak, but it was just a logical error that we never destroyed the weak pointer, still observing the object. So beware of that. If you have that situation, don't use MakeShare. Do it in 2 steps. Call new and then assign the ownership to a shared pointer so that over a long period of time when the object was destroyed, the last owner was destroyed, you can still use the weak pointer and you give up the memory. Okay? Good. So only if we then destroy the last weak pointers, then we will free the whole memory. So that's the first thing. Let's talk about a few other things. One of my things is, well, we came from an example motivating about polymorphism. So we had an example where we have geo-object, circle, and line. So interesting question is, first of all, can we use smart pointers like ordinary pointers? And there's one thing you might know, that which is the is-a relationship. We can say a circle is a geometric object, a line is a geometric object, so we can use them as that one. There's an important rule when you use inheritance, which is is-a relations, inheritance relationships don't propagate to collections of the types. So if you have a base class like geometric object, and you can say a circle is a geometric object, it does not mean that the collection of circles is a collection of geometric objects. Because a key API of the is-a relationship, a key feature of the is-a relationship is that you can do everything with the derived class you can do with the base class. So if you have a collection of geometric objects, what can you insert? A circle and a line. If you have a collection of circles, it would not be very well if we could insert a line. So that's the usual logical rule we have, and that applies to inheritance and the is-a relationship in general. And thanks goodness, we have implemented that in C++. You can see that. So if you create a vector of geometric objects, if you use a base term, so a geometric object pointer, you can push back a circle pointer and a line pointer. That's fine. But if you create a vector of circle pointers, you cannot push back a line pointer. And that is implemented in the logic of templates. The way the standard, the language can do that is they say, if there is an is-a relationship between types, this relationship does not propagate if I pass these types as a template parameter. That's the way we realize this rule. And that applies to everything. That even applies that if we use a collection or just any template, if we use any template that there is no relationship anymore between types like being inheriting or saying this is a const version, so that there's an implicit conversion from a non-const object to a const object, etc. So we have to implement that in our types, which we do in some times, and so we need some support also in the template code to program that. And that's a safety feature that this does not work. Yeah, that's not to blame you. So therefore, we had to implement new dynamic cast operations for shared pointers. So, and we had to introduce a dynamic pointer cast because a shared pointer is also just taking the type of the elements. So we have a problem with propagating the is-er relationship to the template types, to the templified types. So here it is. If you create a vector of shared pointers and you push them back, the element you have, if you ask it, what are you? I'm a shared pointer to a geometric object, and you can't directly use it as a shared pointer of circle, as it's always the case with pointers, but you can also not dynamic cast, so downcast it with the keyword dynamic cast to its downcast to the type of circle, again, to implement some special behavior. We had to introduce a new dynamic pointer cast, a new operator, and with that, things work. And that does not only apply to downcasts, that also applies to the other casts. So therefore, we have in shared pointers static pointer cast, const pointer cast, and since C++17, we also have introduced reinterpret pointer cast, which I would always, which is at least as much as a smell as a reinterpret cast alone. Okay. Yeah, this slide you should not see yet. I screwed up the order. Good. Anything else to talk about? Yes, there's one problem left. One problem is don't create multiple shared pointers of the same raw pointer, because then you have two objects thinking they are the only owner of this pointer. That's another good reason to use MakeShare if you don't use weak pointers, because you don't see raw pointers at all. So you don't fall into this trap. However, the problem is we can't easily avoid this trap if we just use objects. And for example, a member function of our object shall return a pointer to this object. We want to avoid raw pointers. So let's return a shared pointer of the object. And that's not supported because a shared pointer is a wrapper around an object. And now we are asking for that the object returns this wrapper type. So we have a cyclic dependency between things here. The way to support that, which is a workaround and it does not always work well, is that we have a base class enabled shared from this. And this enabled shared from this class, let me see. Let me animate what it does. So this means that you have to derive your data type from a base class enabled shared from this. And what it does in the base class, it creates a weak pointer for you, which is initialized with a null pointer. And then, if you then create your first shared pointer, this weak pointer becomes a shared pointer or becomes a pointer that owns this memory. It doesn't become a shared pointer. So, by the way, that means before you didn't create a shared pointer, you can access usefully the shared pointer from this object. But the moment you have it, you can call shared from this. And if you call shared from this for an object, then this will give you a new shared pointer using the same control block. As I said, that's a workaround. It has some impact because, for example, you have to derive from another class now. It has interesting problems if you have multi-inheritance. It's a workaround. It's kind of a hack. It works in many cases, but not in all. So yeah, we are feeling a little bit uncomfortable already with shared pointers, but it gets worse. Performance. Let's look at performance. So first of all, we have some overhead. We have this control block object, which has to be allocated on the heap. Something like, I don't know, I measured somewhere, but that's not approved, 16 bytes, maybe 4 additional bytes if you have a non-trivial deleter there. And using MakeShare usually saves 4 bytes, and usually deriving from enable shared from this, you might add 8 bytes to each object, something like this, something around this corner. So some overhead, and for each shared pointer, 1 call on the heap if you don't combine them with MakeShare, which has its own problem. So, but we have another problem. And the other problem we have to talk about is multi-threading. If we have the following situation, we have a shared pointer declared SP here, and this shared pointer is used at the same time in 2 different threads, on the left, on the right. So the thread on the left pushes it back into a vector. The vector creates a copy, therefore. And the thread on the right passes it by value to a function, which also means we copy the shared pointer. So the problem we run into is the following. We have an object owning a resource, and now at the same time 2 threads try to copy this shared pointer, which means at the same time they want to increase the ownership of this pointer. That's not good. Distributed programming and multi-threading is good as long as you don't have to share the same object. Otherwise, you pay a price because you have to send around the data, and even worse, you might have to synchronize the access to that data. And that's the case here. And we discussed whether we want to have it or not. In the early implementations of shared pointers at Boost, this was not synchronized. But during the standardization, we came up with a defect. You see it here, 896 it is. And this defect was discussed. And before C++11, we decided that we give the guarantee that you can use, that you can count on the fact that it is safe to copy a shared pointer. That's not that in general shared pointers are thread safe. So all the operations, all the other operations, you have to synchronize. But just copying a shared pointer is thread safe. You see it in the last sentence here. Changes in the use count do not reflect modifications that can introduce a data race. Data race is our term for race undefined behavior due to a race condition. Good. So that's new. Good. What is the price? Well, the price is we have to do something with the implementation. Because that means that if you go back to the slide here, that means that our counters have to somehow synchronize the access, which means they have to become something like atomics or mutexes. Just a side note, what can happen is that one thread deletes the last owner and another thread deletes the last weak pointer. So both threads think there is another thing when they decrement, but at the end we have the 0-0 situation where we had to delete the control block. So therefore, we not only have to synchronize between threads the owner counter and the weak pointer, we even have a dependency between them. So we need some logic of a protected region between them so that whenever one of the threads is the last thread, so that both owner and weak pointer gets to 0, then we have to delete the control block. That can be improved. Usually you don't use mutexes because they are pretty expensive. So a way to do that is that the weak pointer in practice is not a weak pointer. It is a pointer that also counts how many owners we have, or says, I add 1 for at least 1 owner. So we say we have an owner counter and we have a weak and owner counter. because then we don't need a protected region to decide whether we have to delete the control block. Then it's enough to see whether the weekend owner counter decrements to 0. Okay, so it's tricky, more tricky than we think. So we have that in the standard, and atomics and synchronization between threads and mutexes are expensive. So the question is, how expensive are they? I have provided a program here, and the program, let's see. The program does roughly the following. I have 1,000 elements. I have counter for 1 million iterations. And what I do, I initialize a vector of 1,000 elements, so 1,000 shared pointers, referring to an object. And then I start a loop. And in this loop, I do 1 million iterations over these 1,000 objects, and I perform a simple increment call in all these objects. I make sure that the objects are not shared, but the iterations over the shared pointers might be passed and used by different threads. And now the key point is, while I'm iterating over the shared pointers, I can switch between a loop using auto-reference and a loop using auto without a reference. Without a reference, we would copy all the shared pointers. Without reference, we would copy the shared pointers. With a reference, we would never copy any shared pointer. And that's an example program I have, and let's compile and run it. So here we have it. Oh, wait a minute, I switched the mode because I don't see what I'm doing here. I don't have a monitor here for me. So I come back. So yeah, now I see it. Good. So let's compile it. Make shared pointer loop .14. That will use GCC 5.5, as you see, with -02, and again C++ version 13 compiler. And now we can use this program, shared pointer loop. It has a couple of options. So let's start with having one thread and iterating by reference. Once again, we iterate over 1 million times over a vector of 1,000 shared pointers. And I made sure that the operation is not optimized away. There is an operation that is called and that gives a result. And here is the current output, 4 milliseconds. Let's switch to iterate by value. Nah, that's wrong. That's a little bit slower. So maybe you have heard about the overhead, but maybe it surprises you a little bit how big the overhead is. Please note that there's a 1. I only use one thread. That means here you see how expensive it is to generate assembler code that synchronizes with other threads, although there are no other threads. Yeah? And now you know why the Intel guys who introduced this new feature that they don't synchronize threads unless they have to, they suddenly got a factor of 10 or 100 or 1,000. So let's use 4 threads. By reference first. Pretty much the same as before. You see that the output is screwed up now from the 4 threads. It seems that here the amount of the cost of starting additional threads pays off with the fact that each thread has to do less and we can do things in parallel. So I divided the 1 million iterations through the 4 threads. So each thread does only 250,000 iterations. So now let me start a task manager, because that's funny. Here it is. Now let's use 4 threads and iterate by value. Yeah, let's drink a coffee. But you also see another problem. Yeah, the CPU is stalled. What you see is what it takes for CPU now constantly sending the counters around, the 1,000 counters around, back and forth between the different cores. That's the price of a shared pointer. And it's a funny story how I created this talk. When I created this talk, the reason I created this talk, I was sitting in a C++ conference in Aspen, and on stage, somebody was saying, here, this is a cool shared pointers, and you know what? Some people pass shared pointers by reference. That makes no sense, because it's just a shared pointer, it's a pointer. So why should you pass it by reference? So I phoned up my chief architect from a project I was currently in, and I said, why do we have the rule always pass a shared pointer by reference? Because they say that's stupid. And he answered, they have no clue. And here's the reason. You saw that. And there's a real story behind. It was a project where they invented a new database based on using many threads. And this database had to scale, and they used shared pointers everywhere because they thought it's a good programming paradigm. And it turned out, when they started to use it in real practice, the database got on hold because they were only sending around shared pointers. And this is not the first project I know now. That happened to a couple of projects that they thought, oh, shared pointers, there's no problem. Let's use them everywhere, and that's good. So you see the price here. So yes, it's not against shared pointers. Use them, but use them with care, and especially don't pass them around by value if you can't pass them around by reference, because then they are as fast as raw pointers. Good. So that's a price. That's a real price of shared pointers, and you should know it. Wait a minute. I want to switch back to my normal presentation mode. Now the interesting thing is that my presentation is gone. We have different numbers. It's not the exact factor that counts. We have different numbers. Here's in the project where I just talked about, we also did some measurements, and we saw that the overhead was about factor of 40, and with minus 0.3 it became a factor of 80. This was using 8 threads on the Intel Core something, and you could see that 82% of the time the CPU was waiting to get access to an owner counter. That was the problem, so it was stalled. And if we passed the shared pointers by reference, we were only waiting 16% of the time. So that's the point with shared pointers. Good. So pass them by shared pointers. That's the first lesson. Or is there something better? Yes, there is something better. That's unique pointers. So let's look at them first, how we can use unique pointers here. Let's start with our basic example, polymorphism. Here we have them with shared pointers, but let's switch to unique pointers. So what's the difference with unique pointers? Unique pointers, you can use like shared pointers. Instead of make shared, you call make unique. The type is unique pointer instead of shared pointer, but there's a difference. They don't count. And they don't have to count. The question is, when they don't count, how do they know when the last owner dies? The trick they use is, there can't be a second owner. That's all they do. They say, we make sure that there's always only one owner. And that's an interesting trick because you can enforce this trick at compile time. You don't have to do anything at runtime. All you do is you disable copying. And that's what they do. And that's why this program now needs, you see that, a move. Because it would not compile if I call pushback to push back this pointer into a vector. We make sure that if you push back the unique pointer into the vector, this will be moved. The ownership will be moved into the vector, and the ownership of the circle pointer will be moved. And when we then return the whole thing, then because we have move semantics here, when we return a vector of elements, we have move semantics, and that means that we move the elements to the one who gets the result. Because the elements in the vector are dying where we move the elements from. So we don't have to do anything here. So let's use them as before. Let's iterate over them with polymorphism. And please note that you can now not compile iterating by value. You have to iterate by reference because it's not allowed to copy a unique pointer. And the good thing is now when we call clear, it's easy. Each element, each unique pointer knows whether it is an owner or not. And if it's an owner, it can only be the only one because it's not possible to screw that up. Well, it is if you pass a raw pointer twice to two different unique pointers, but then it's your fault. So we can then safely delete the pointer. Okay, and if you don't like move, call make unique and pass it directly to pushback. And you have the same effect. So that's a cheap raw pointer. That's one of the few cases where we create significant more safety without overhead, without performance overhead. Because the type system is our friend. And we introduced that in C++11. We couldn't introduce that before C++11 because we needed move semantics for that. Our first try to implement move semantics in a shared pointer was called auto pointer, and it was a nightmare because we thought we could implement move semantics in the copy constructor of an auto pointer, and that created some interesting problems. So if you have an auto pointer, replace it by unique pointer. If it still compiles, fine. If not, fix the places which might either need a move, or you have a code smell, or you have abused an auto pointer. And you have found a bug. Okay, that's a unique pointer. Unique pointer, to explain a unique pointer, that's easy. We can create it. We can create a resource. We can pass the ownership to a unique pointer. You can't pass the ownership to another object, but you can move the ownership to another object. And that's the benefit of a unique pointer. No overhead. Everything is decided at compile time. Good. So the trick the unique pointer is implemented is simple. We have deleted copying, so we have no copy constructor and no assignment operator, no copying assignment operator. We only have the moving operations that do what you just saw. By the way, make unique was not available in C++11. We added it in C++14. So before C++11, you had to call new and pass then the ownership to a unique pointer. So are there any problems? Of course there are. Always there. It's not a performance problem, but we have some restrictions. I think the biggest restriction we have is it's not that easy to have polymorphism. Well, that's easy, but to have a downcast back to the original type. So if we have that here, everything works fine, create a unique pointer, push back, everything is fine. But if you then assign this to oh my goodness, this slide is wrong. But I'm pretty sure I made it this morning at 5 o'clock and I fixed it. But it seems I didn't. Let's see. Probably it's here. This is screwed up. Let's hope the best. Yes. Good. So, so if you then access the first element, first of all, auto would not work here because you would create a copy. So you have to use const auto reference, and the type is a unique pointer. But you can't cast down, and we also can't create something like a dynamic pointer cast or dynamic unique pointer cast, because what is the essence of a dynamic cast? It downcasts you the pointer and gives you a second pointer referring to the same object. That's by intention exactly what we don't want to have in unique pointers. We don't want to have two owners. So we simply can't provide a downcast operation for unique pointers. So that's probably the biggest drawback. And that means that you have to use dynamic cast. And the way you can use it, you can access the raw pointer behind the unique pointer and then call downcast. And please beware that you don't use it longer than necessary. So because we have lifetime issues, and never pass this to something like another location where people might create a unique pointer or shared pointer from that. So that's the way you have to do it, and to make it a little bit more safe, you might say, let's do it in one expression. So in the if statement, you can declare with auto the circle pointer and use it, but this makes sure that at the end of the if statement, the lifetime of the raw pointer is gone. So beware. And it's a problem to return a unique pointer for an object that exists. We don't have support for that. Yeah, that's a price. There's always a price. There's no free lunch. But the good news is there is, regarding performance, no overhead. And that's a very important aspect in our programming community, because one reason we have C++ often is performance. So if you can use unique pointers, use them. End of discussion. You have to explain me, if I see a small shared pointer, that's a smell. You have to explain me why you don't use a unique pointer. There's another interesting issue here, a last issue here. As you can move around ownership for unique pointers, you can do the following. You can say, hey, wait a minute, inside a function, I create a resource, I pass the ownership to a unique pointer, and I pass the ownership to the calling side. So that's easily to do. You don't need any move there. Just return it by value, because this return by value is a call with move semantics, because the local object is about to die. So the calling side can, in a loop, call this function. Each time it calls source, it gets the ownership of the created resource that was created there and can use it. And the next time you, in the loop, call source again, you delete, because you are the owner of the previously returned return value, you delete the ownership, so you call delete for the created resource, and you then become owner of the next return value. That's fine, that's safe programming. And it's also possible the other way around. You can say, let's pass my ownership to a function. What you do then is, for example, here in sync, you declare that you take the ownership of a unique pointer. So the caller then has to pass an ownership by calling move here. Without the move, it wouldn't compile, because then you would create a copy here. Now, there has been an interesting discussion in our community between two of the guys we usually ask if we ask for style and good programming practice. So this is the Herb Sutter style, I call it. Because Herb Sutter said that's the way you should do it. declare the unique pointer in the sink to take the unique pointer be taken by value. And then came Scott Myers and said, no, that's not the way you should do it. You should pass it by R-value reference. Because obviously we have here move semantics, so you should signal that in the signature. And they started to discuss that. And I think finally Herb said, Scott Myers were right, but I don't agree with them. I think it's more complicated, because this is a nice demonstration of the feature move semantics. First of all, both is possible. The difference is, if you pass a unique pointer to a function taking it by value, you will give up the ownership. Okay? Because you create a new object, this object gets the ownership, this object is destroyed at the end of the function call. So as a result, in the first part, if you pass it by value, you no longer are the owner of the resource. And it was freed. In the second part, you only pass a reference. And if you pass a reference, that means you refer to the original unique pointer, but it depends on the implementation of this function, whether you use the ownership or not. So it's funny with move semantics. If you don't signal move here, so not having 2 ampersand, it will move. If you signal move here, it might move. That's one of the interesting aspects of move semantics. There are good reasons for that, but in general, the lesson learned here is pretty easy. The lesson is, if you have marked something with move, it might or might not be moved, because the specification is after using a move from object, the object is in a valid but unspecified state. Well, for unique pointers, we even specify the state, but I think it's good style not to break this rule in C++ just for unique pointers, which, by the way, some people try now by even adding more interesting interfaces. So if it's important for you that the ownership was gone, don't count on the fact that sync takes the argument by value. Or don't count on the implementation of this function if you pass it by reference. Make it clear that this is your assumption and your will. And the way to do that is, after calling sync with move, you say, I'm no longer interested in the resource, in this value. So the right way to call sync, however it is declared and however it is implemented, is call move and then call unique pointer release. That way you make sure and you have expressed explicitly that it is your will that you are no longer interested in the value of this object, and the corresponding resource should be freed. And you can be sure that it is freed. Please keep that in mind. Style guides are like this, are really missing. We have a problem in C++, we have many, many new techniques, but we don't have corresponding style guides, which we only learned over the past years. We had very early a book called More Effective Modern C++, but that was written 7 years ago. We need a new book. A lot of things have changed looking back with C++ 11, which we should have teach to users now, especially regarding move semantics. Good. Final comment. Yes, there is an intentionally very different approach and design for shared pointers and unique pointers. Shared pointers were implemented and designed to have no performance overhead. End of discussion. While shared pointers anyway needed overhead, because of the reference counting that had to be stored somewhere. There's no way to go around that. So we could say, yeah, it's safe, and we can share ownership between different places, which you use a couple of times in your programs, but they have an ownership. And you see the difference in the way you pass a deleter. If you pass a deleter, your own deleter, to a shared pointer, it's enough to pass this deleter in the constructor. So here, again, the pclose, which we pass to the shared pointer despite calling popen. If you have to pass the deleter to a unique pointer, you have to pass it twice because the type of the unique pointer has to transfer it somewhere. You need to make sure not to confuse different unique pointers having different deleters. It should become part of the type, and also to be able to store it there so that the unique pointer suddenly has some memory, some member for this type, for this member. So therefore, you have to pass it twice, once as an additional argument, the type of the deleter, and once in the constructor, which can be improved with C++20, because in C++20, it's allowed that we instantiate a lambda later on, provided it has not captured anything. So there, the second, you don't have to pass it in the constructor, but the difference will remain. The shared pointer needs a deleter in the constructor. The unique pointer gets a deleter as a template parameter. That's the difference. And yes, we know that difference, and yes, we apologize, but it's the price of having very different interests and implementation mechanisms for shared pointer and unique pointer. That's the way it is. We can't resolve that easily. That's it. Thank you very much. I hope this was useful. I'm not long time here around, but for some questions, I'm around here for a few minutes. And yeah, Merry Christmas, and if we don't see until then. Thank you very much.